And Reza Rokni, developer advocate for Google Cloud Dataflow, and I work a lot with Apache Beam. So for today, what we're going to do in our agenda, the agenda we have for you is going to describe a particular problem that we were trying to solve in building out an application. It is the data source is streaming time series, and we'll go through the specifics of what we were trying to achieve. After that, we're going to do a high-level overview of TFX, which Robert will do for us, including describing a little bit around the model, because the bulk of this talk is around data engineering needed to achieve our goals. Then we're going to walk through the architecture that we came up with, and then I'll do a very short demo, demo gods being on our side, including a little bit of tips and tricks on things that we found very useful when we were building things out. So in terms of the use case, they have 4 objectives that we wanted to hit. The objective 1 was actually a streaming Dataflow pipeline, Apache Beam pipeline running on the Dataflow runner, which is converting time series information into metrics. There were 2 types of metrics that we wanted to generate. The first, the type 1, is a metrics within a fixed window. So for an IoT device, this would be the min, max, last, first values within, for example, a 10-second time slice. And for market data, it could be something like open, high, low, close of a stop value. Those data points will then be fed into a second sliding window. So the fixed window is moving onto the sliding window. And that's our type 2 computations. The type 2 computations are things like absolute loss, absolute gain, where we need an ordered sequence of data from our first computation. We are mentioning the word order there, which should always make us go when we're talking on a distributed system. However, because things are going first through a fixed window and we're putting it into a temporal time of, say, 1 second or 10 seconds, the problem becomes very manageable. So into a little bit more detail on the computations. In this example, the gray circles are our data points. The solid line is our fixed windows. Let's say they are 10 seconds. And the sliding windows are our broken lines. What we're going to compute is 2 metrics. One is the sum within the fixed window, and then the absolute gain between values coming from the fixed window side. So in the first instance, we see a sum of 2, and then 3, 4, 2, and 3. These are essentially just adding up the gray circles that we see within our fixed time slice. The second sliding window is actually doing the difference between the first and the second value seen within the fixed windows. So we have 2 and 3. That's an increase of 1. It becomes 1. Next up is 3 and 4. That's an increase of 1. Again, becomes 1. Next is 4 down to 2. So that's a loss. So in terms of absolute gain, that's a 0 being recorded. And if you'll notice, the sliding windows are actually aligned with the fixed windows with the offset. So the next sliding window moving exactly 1 fixed window length forward. With that pattern, we can actually merge this data set together for the downstream computation. So the array that you see coming out of there is the 3 from the fixed window, so the second value, and the 1. So 3 and 1, 4 and 1, 2 and 0, and so on. So this is the metrics that we are computing. For our second objective, so once we produce those metrics and send it on to the other teams, the second objective is to actually build a model based on an LSTM autoencoder and decoder. Robert will be discussing a little bit more about what that model does. And I was working with a data scientist who was working on the model side. I was doing the data engineering work. For me, the most important piece of information that he had to give me was what does the shape of that first input layer look like? And for an LSTM model, it is essentially the shape we see here, which is the number of time steps from now into the past and the number of features. In the previous example where we had sum and absolute gain, we had 2 features right there. And so that you have 2 blocks. And basically, these blocks would move forward in time based on the offset of the sliding window. And this is the data shape that I need to get to the LSTM model. Specifically, we were using the model to do anomaly detection. The third objective is to have the inference running continuously with the model that was built in the previous step. So we want to be able to not only produce metrics for our other systems, we want to run inference and detect potential anomalies all within the same system in a streaming mode. And the final objective is to retrain the model. TFX is in batch mode, so retrain in batch mode the model periodically, whether that's based on time or number of elements. Those are different signals that we could use. But essentially, once the model is retrained in batch mode, to be able to get the model into our inference system and continue with the new model with the data that's coming in. Okay, so just to recap, converting our time series to metrics, creating an STM encoder decoder, and objective 3, running the inference, and finally retraining the model. A couple of things. So in terms of the time series work, and we don't go through the details of it in this talk, we're doing some fairly edge case stuff. For example, we're using looping timers. There is a blog post on looping timers on the Apache Beam site that you can go to. Essentially, looping timers allows us to do things like gap filling. So when the time series, there's no values, we can either put in a 0, a null, or take the last known value. And we use state and timer APIs to do that. So these are fairly interesting uses of the Beam model. There is a matrix on the Apache Beam site on different runners' specific capabilities around lifecycle management, for example, that may not support looping timers. So that's why we have Hebe dragons, although it's a very cute dragon. Another thing, in terms of our TFX side, when we started working on this, TFX did not support TF sequence example and it was supported TF.example rather than sequence example. So both of those are the proto definitions that you can serialize data into for training or inference. Sequence example is used for sequential data like we have here. And because we didn't have that, we actually used the TF example and used the features there to simulate the sequence example. Good news is, and I think Robert may have a chance to talk about it here, but if not, I think very recently TFX is supporting sequence examples, so I will be going back and redoing some of the workarounds we put in place for that piece. With that, I'll hand over to Robert to give us a little bit of overview of autoencoders and also, more importantly, TFX, the pipeline we use to building our models.
Right. Thanks, Reza. So we're using an autoencoder here to look at the data, and essentially what this does is we have two parts to it, or maybe sort of three parts. There's an encoder at the beginning that encodes the input data and learns it. And it's compressing it down to hidden layers. So it's taking the input, essentially denoising it and compressing it down. And then in the decoder part of things, we kind of reinflate that data. And the goal there is to try to duplicate or train the model to duplicate the input data. And then using that, you can look for anomalies by looking at the reconstruction error. So where your predicted data is different from the actual data, you can see that there's something that's different than what the model learned. And you establish a threshold for that and say something above this threshold, however you define it, is considered an anomaly. Fairly standard approach, really, to anomaly detection. It's one of the, especially for nonlinear, it's one of the more common ways of doing anomaly detection. Next slide.
It's being a little bit slow. There we go.
There we go. Okay, let's get into a quick overview of TFX. If you're a data scientist or a ML engineer, typically the first thing you're focusing on is your model. You're thinking about the results you're trying to generate, and you're going and looking at different models and reading papers and so forth, or maybe you have certain models that you're already using. That's great, but when you put something into production, next slide, you discover that a model is, we've measured it as typically around 5% of the code that you need to develop and maintain. And the maintenance and keeping this thing running reliably over time is a big part of the task. So you start to become familiar with the difference between a model that you train in maybe a notebook and a production software solution. Next slide. And people have kind of learned this the hard way. This is kind of a famous tweet from Gina Blabber over at O'Reilly. Um, it's actually, unfortunately, all too typical, where people have a model and they figure, oh, I'll have this working next week, and then 11 months later, it's still trying to get the thing into production. Next slide. So, thinking about the challenges you have in machine learning development, you have all the standard challenges you always have. So, assuming you're doing supervised learning, which is a little different in the case that we're looking at, we're not actually using labeled data so much. So that's a little different, but definitely a factor. Worrying about your feature space coverage. Again, this particular example is a little bit different because we're using the direct data coming in and trying to reconstruct it. So our feature space is sort of covered by default. Minimizing dimensionality, fairness, and rare conditions. In this particular case, rare conditions could be catastrophic. If you have, depending on what you're trying to do, it could be either a missed opportunity or a significant loss. So that's something to think about. But in production software deployments, you have a whole lot of other things to think about. And the minute you put ML into production, that's what you're doing. So how are you going to scale this thing? How are you going to manage things like modularity? And how are you going to test your code? It all becomes a little more challenging than just doing something in a notebook. Next slide. So that's why Google created TFX in the first place, originally because we needed it for what we do. And we use TFX all over Google. So you'll recognize some of the icons here. It's, for most of the ML solutions that we put into production, we're using TFX. There's some special cases where they've built kind of bespoke solutions, but mostly we're using TFX. And now TFX is available, has been actually for a couple of years now, as open source. So next slide. Yeah, actually next slide. So there's different layers involved in TFX, or really any ML pipeline. If you look at what the CD Foundation does, it's very similar to this kind of an architecture where you have, sort of base layers doing things like garbage collection and managing metadata and so forth, and then different phases of the process represented as tasks, or in the case of TFX, they're components, and then UX on top of that, and so forth. Next slide. And these are the parts that are included in TFX today, the orange components there. So we'll go through that a little bit, but we're kind of limited on time. So I encourage you to go to the TFX website for more details and tutorials. Next slide. So one of the ways to look at this, and you can kind of turn it around in different ways, is to look at how this is structured in terms of the libraries and the components that are built from those libraries, and some of the libraries which are powered by Apache Beam. So going from left to right here, we have different components involved in different parts of the ML process, from data ingestion through really analyzing your data and training a model, and finally out to your inference target, your maybe TF serving, or it could be a mobile application, or what have you. And along the way, we're using Beam and leveraging distributed clusters of compute resources to do that processing. Because remember, this is designed to work with large amounts of data and potentially very complex amounts of processing. Next slide. So starting at the beginning, this is example gen. This is the first component. In a pipeline, it's just ingesting your data and then converting it to TF examples and splitting it. And you can configure the splits you want. And this is showing just two data sources, but there's a list of data sources that are available. Next slide. Moving farther down the pipeline, we have transform. Transform is all about feature engineering. So it's where you're going to do the transformations on your data to really try to do two things. You're trying to improve the predictive content in your data, and you're trying to make it as efficient as possible to process, especially for inference. And one of the key aspects of transform is that it produces a pre-processing graph. That graph is going to be bundled with your trained model, and that's going to be used wherever you deploy your model to do exactly the same processing. So next slide. So that processing is really consistent, and you don't have training and serving skew. And this is Apache Beam. I think you guys are probably pretty familiar with Apache Beam, I'm guessing. But it's used by TFX in several of the components to do, distributed processing on compute clusters. Next slide. So for several of the components, we're using Apache Beam to do that processing. So when we need to split a data set, could be a big data set, or when we need to do the feature engineering that we just talked about. Again, it could be a lot of processing, and we need that distributed cluster to do that. Next slide.
Okay, thanks. Thank you there, Robert. So yeah, the nice thing there with the TFX, obviously, anything that we build in Apache Beam can run on any of the execution environments, whether that be Dataflow, Flink, etc. In terms of the architecture that we built up for this particular piece, remember the first objective was to actually take the time series data and produce metrics from it. For that, we used a Java Beam pipeline, and we output metrics in two different locations. So the first one, which is our key objective for number one, is we're processing this data and producing the metrics to Google Cloud Platform. This is then going on to downstream systems that are making use of the metrics that we're generating. So those type 1 and type 2 computations. So that is using those things like looping timers and stuff to get the data in very good shape. We're reusing that exact same data to land TF record files within Google Cloud Storage. And that is because we want to achieve our second goal, which is to be able to build a model. So we now have equivalence between the data that's coming into the model building and things that we're producing in general for the rest of the systems. Here, the TFX pipeline then can consume those records and from TF record and make a model using the LSTM model that we have in place. At the end of the run, so after it's run through most of the components, and there are obviously many more components than the ones Rob just talked about, but those were we concentrate on that just due to time, and also it's interesting for the next couple of slides. So it will do the example gen, it will do the transforms, it will then do the training, and the model that we produce also contains that transformational graph that Robert just talked about. That model lands into Google Cloud Storage, again, an object store, any location that we can then pick up using our Python part of this pipeline. So the TFX team has something called TFX BSL, which contains a inference module, so the run inference, and that's available as a Beam transform. So we can plug that directly into a Python stream processing pipeline and allow us to run inference against the data that we've sent into our publish and subscribe API. Of course, that could be Kafka instead of PubSub as well, or any medium for getting the information from one side to the other. The interesting thing here, tying back to what Rob was saying around the transform. So we're doing something slightly different from the norm because we are doing the metrics creation is essentially, those are still features that we've created, right? So those are, that's kind of processing that we're doing. And it's very important that we keep the idea of the thing that Robert described between the training side and the inference. So just talking through, again, the bits that TensorFlow takes care of for us when we're using TFX all the way through, we obviously consume our raw data, as Rob was describing in example gen. And then in transform, we're actually doing that feature extraction. However, because we are actually doing quite a lot of that work in the Java pipeline, we need to be extra careful because we are no longer getting the stuff that we normally get for free from TFX. So TFX provides this hermetic seal between the way that the transformation is done in the training mode and the run inference, because that transform graph becomes part of the model. In our case, because we're doing some of that work outside of that, we need to make sure that we try and follow the same principles. So one of the ways that we did that is the records that are landing in cloud storage, we show them as a TF example. The ones we send to Cloud PubSub, we actually have them also as TF examples. We just serialize them to JSON. So we're trying to keep things as exact as possible between the two systems. Again, because we can't use we've gone a little bit away from the norm. And in terms of limitations that this brings to us, so one limitation, which if you're familiar with LSTM will be very clear, but if this is the first time you're dealing with LSTMs, again, it comes back to the number of time steps that we have. So within the Java pipeline, we can't change dynamically the size of the sliding window. Therefore, the number of time steps that are in flow are fixed. If the data scientist comes back to me and says, Reza, I need a different size of time step for the model that I'm building, then we would need to rebootstrap the system. So we need to restart the Java process and also reprocess the data that we still have because we're producing all these metrics into a different time step size. The good news is, of course, with Apache Beam, the stream and batch processing is being done within the same code base. So we're just changing the source from unbounded to bounded. I don't tend in my logic, and I can redo the bootstrap. We have a couple of strategies potentially to work around this, but this is one of the things that we take on by taking on some of this work in this piece. So with that, a very quick demo. Let's make sure our demo goes with us. Here I'm showing the data flow runner for the code that was written. And for this demo, my apologies, I forgot to go through 2 slides before getting here. And that is a little bit talking about our data. So for the demo data, we're just using some synthetic training data. And the data is just it's just a wave function. This is the training data, so there is no anomalies here. For the inference data, we will actually have the data have some anomalies. And what we're going to do is, normally the data is between -100 and 100. Here we throw in some values which are way above 100. So in this case, there are 3 occasions where we have thrown some outliers into the system. So going back to this slide. So here we're seeing the monitoring interface for the data flow runner. The 2 transforms at the bottom are actually doing all of the work of processing the time series. The 2 transforms at the top are just generating that sequence for me. So just for the purpose of this demo, if I expand on this transform, obviously, as you would expect, there's a lot more going on underneath the covers. Our generate computation is doing things like doing the gap filling. For example, in this transform perfect rectangles, we have our source of data coming in and it's being split. One source is moving straight into a flatten operation. The other is going through the sequence of steps needed to detect whether there is a gap in the data and then do the right thing for it. In this particular case, if there's a gap, we just fill it with a 0. If this was market data, we might want to fill that gap with the last known value for a particular stock price, for example. And if I click on this particular transform, the fill gaps, we get some information about what's been going on in there, and we can see that it received 47,884 elements, but only 165 coming out. So there's 165 gaps that it's filled based off the data that it's had since it's been running. Downstream, we see some of the computations that are going on against all the data, including some of this type 2 computations, for example, moving average or RSI, etc., as well as the output of this whole system. So if I expand our output, here we see we're writing to 2 locations. So writing to file IO, so we're writing this to our object store at a rate, if we look on the graph on the right, of roughly 1 a second. And that's because the sliding window's offset is set to happen every second. And we're also writing to PubSub at around the same rate. Just a quick note, I've only, for the demonstration, I've set the file write to be every second. In a normal system, going out every second for pub/sub is fine. For the file write, we probably do it like 10 minutes or 30 minutes because those are being used for training, and it's inefficient to just create a file every second. In the next pace, we're going to look at some of the output going into pub/sub. So we're going to see what that looks like. So this is the pub/sub user interface. I have a subscription called outlier detection. And what I'm going to do is click on view messages, which should let me pull a few of the messages off that subscription. Now, let's see how we are doing. I sometimes have to click this a few times. Let's see if the third time is a charm. Yes, it was. Okay, so if I expand on this, we should be able to actually see some of the data that's being generated. This is the JSON representation of a TF.example. We have all of our metrics being generated. For the purposes of the next part of the demo, we're only going to look at two particular metrics, the first and last value. So those are the metrics that we're going to look for anomalies on. We can see here that we were in a downwards part of the curve, and this looks like an anomaly, actually, 161. It's above our threshold, and it's out of sequence. So hopefully that would have been picked up as an anomaly. We can also see the type 2 computations, like the absolute moving average, etc., being computed, even though in the next part we're not going to use that. This stuff is being continuously generated for our metrics creation. And of course, there'll be files landing into our storage location about one every second. For the next part of the demo, I'm going to move over to Notebook. And a great tip, so when I was working with a data scientist, I'd be working in my IDE, and he was obviously working in his notebook and doing exploration stuff. When we were hitting bugs and issues, one thing that I found incredibly useful was to be able to take my pipeline, my TFX pipeline, put it into the notebook, and explore the data. And this is based off of there's a notebook in TFX website. I think it's called the Keras TFX example, where they've all of these steps are there, and we took that as a template. It's a really, really good resource for doing debug work. Importantly, because in this case, for example, we are running the import example gen directly using the interactive context. And this gives us access to the output from each one of these stages. For example, this one has output and I'm running this on my local environment. So here's on my local environment where I can actually then go and explore the data. So using APIs like the TF Record Dataset API, I can actually go and pull information from the files that were generated as part of that component and have a peek at the data that's in there. So here we can see our values looking very similar to the one that we did in pub/sub. This is obviously the representation that we see after parsing it to a TF train example. The other even more useful feature is now that we're in a notebook, we can actually have a look at this data. So here I can see when I've extracted the last and first values, what the data was looking like for training. As we go further down in TF Transform, one thing that we do in TF Transform is here is where we will remove the features that we're not interested in. So, for example, because we've got all these other features, and the only ones I'm interested in is last and first, in our TF Transform code, we actually extract just last and first. And we can see that effect by looking at some of the output of the transform component. This data, this metadata information, etc., is all information that pertains to the spec of the data going into TF Transform. And if I scroll all the way down to see what comes out, so we see lots of values similar to the ones we saw earlier. If I go all the way down, bear with me, please. There we go. We see that in our output, we actually, here we are. Oh, no, finally getting there. Here we go. Sorry about that. So in our output, there's actually only two values, float and label. And as Robert described, the autoencoder decoder, the label essentially is the input data. We can see the time steps, 5, and there's 2 features. So this spec is that thing that's being hermetically sealed with the model that's built. After this, of course, we have a model that, let me scroll down. We have a training model that's run using the training component. In this particular case, we ran it to 30 epochs, and our mean absolute error is down to 1.3. Our range of data is -100 to 100. So at this point, we have a saved model file that we can use within the training. Now, for that, I'm going to move to a different notebook. So here, again, we can explore data before we work with it. And what I'm going to do is, first of all, we'll look at some data where we've done some batch inference with the TFX PSL run inference piece, just to see the data. And then we're going to, at the end, start the pipeline to run a streaming inference. So in this particular case, again, I am using the TF record dataset to read the data that's being made available. So we are running this inference data on a object in our object store, Google Cloud Storage. And looking at the data, we now see that the data we're using for inference, again, the very same wave model. However, we have the anomalies in this data set as well. Scrolling down, we can actually see some of the raw values. Again, by being in the notebook, we can explore all this stuff. We see some anomalies outside of the range of the normal data set that we have. And skipping past some of this terrible code, I usually write in Java, which even Java I'm terrible, so my Python is even worse. But the very nice code here is the code that incorporates the run inference TFX BSL within a standard Beam pipeline. So for those of you who've been working with Beam, this will be very familiar. And this one single component, it takes the model that is created. So this model, the file is on an object store. It uses that model to convert the data that we're reading. So in this case, it's batch mode. So we're reading TF record files, and it does the inference. So it's going to produce the output of that decoder for the next steps. The bits of code that I scrolled past are essentially how we process that information. And in terms of detecting our outliers, I will show a little bit of this code. Here is the code that after we've extracted all the bits from the dictionary of information that comes back from the run inference, we then apply our check. What is an anomaly? So in our case, what we have is a threshold value of 2. Remember, the model was down to like 1.4, I think. So we say anything over a difference of 2 between what was input and what the model produced, we're going to consider an anomaly. And what we do, if it is an anomaly, either in the first or last value, is I set a 0. The reason I set a 0 is just for graphing. It looks nice on the graph as we see a clear location when we put these things together. So when this is run, and I won't run it now because it takes a little while, I'm using the interactive runner here, so I can collect the output of that P collection, and we can have a little look at the data. This is the raw data, but let's skip straight to a graph. So here we actually see all the points where it detected an anomaly, where it thinks there was a difference based off our threshold of 2. So there's 3 clear areas here and 1 item here, which actually turns out to be a false positive. And I'll explain why there's a line of these in a moment. So this is where the model is predicting based on a threshold of 2 that there are anomalies. If we join the input data with the data from the anom, we can actually see that it's actually pretty close. Here are the outliers, our 3 outliers, and here are where the anomaly clusters are. And the blue is now hidden here, but that's a false positive. And when you look at the actual number, it's like out by 0.3 or something like that to the value we have. Why we're getting a cluster? If I go back to the raw data, and we see some values around, there's none, yeah, here's some. If you recall, we're sending sequences of data. So we're sending like 8, at this point, 5 items at a time. When we get one of these bad values or these outliers, it's going to perturb the model for as long as it's within that sequence. So for up to 5, and actually because we're using first and last, for just over 5 number of time steps, we're going to get anomalies, which is why we get that clear line. So next, I'm going to actually do this in stream mode. So the beauty here is the run inference is exactly the same because of Beam's ability for the business logic to be the same across stream and batch. All I do is I change the input from the bounded source to read from PubSub, and we're passing that JSON message. So I'm going to run this and see how we do. So this is going to create a PubSub topic. It's connecting to a PubSub topic, so it's going to create a subscription, and hopefully we're going to start seeing some output in a moment. And what we'll see is a lot of output. This is because there is a little bit of backlog in that subscription, so it's going to start reading that as fast as possible. And here we see the values coming out. These are the raw values that were input, and it's not detecting any anomalies there. As we move down, there's some anomalies slowly being detected in this cluster, and we should see, here we go, in the cluster we actually see this anomalous value 167. So looking around, we should see a few more. There's 167 here. Because there was a backlog in the log, it doesn't necessarily mean that this is all going to come out ordered. Once it's cleared the backlog, we should start seeing things appearing just 1 second at a time. So with that, I'm going to move back now to the slides because we've covered quite a few of the things that we wanted to show. So here we have the graph, we have the outliers and the anomaly. So we did objective 1, we did objective 2, and we did objective 3. However, we haven't covered objective 4, periodically retraining this model and updating the inference. So in terms of the retrain, because we have this TFX pipeline and there are other orchestration systems, other orchestrations we can use, we can actually tell it to retrain based off different signals that we have. And that actually, TFX makes that pretty straightforward, and it will generate our state model file. Where it gets a little bit more interesting is around the inference. So how do we update the inference model? Now, this depends on how we are running our inference. The run inference code I showed you has 2 modes. In remote mode, it's actually making RPC call out to an endpoint. For example, Google Cloud ML has an endpoint that you can call. And if that's the way that you're doing it, when you push an update to the endpoint, the system just automatically will then be using the new model. Any in-flight RPC calls that fail will just get retried, and everything's great. On the local model, it's a little bit more tricky. So the local model, it's caches the save model, so we can't get it to update the model directly. However, we can use lifecycle management from the runner. So for example, you could use a drain operation along with a start again to drain the pipeline and restart. On the restart, it's going to pick up the new model that's available on the object store. Or if there's tolerance available for it, canceling it and restarting it with the source being replayed. In the diagrams, we saw Java pipeline and a Python pipeline, and those were 2 separate pipelines that were running. Obviously, with cross-language, which I hope you've heard about a lot from the Apache Beam talks this week, we should be able to collapse all that into one, and that's one of my tasks actually for next week. We really skimmed over the TFX stuff. So there's a lot of great talks, including by Robert, that you can go and look and really get into the details. And with that, I think we're pretty much close to time. So thank you very much for joining us and giving us your time. I think we have a forum for some questions. Oh, Matthias, go ahead.
Yeah, that was a very interesting talk. Thank you, Reza and Robert. I really loved the live demo. So thanks both of you for sharing, and all that while it's already early morning in Singapore. So are you still happy to take a few questions now?
Yes, I can take a couple, and I think there's one already about what are the steps needed to bring the TFX pipeline to the notebook for debugging. So as I said, the template that is there, and I believe, Robert, it's the TFX Keras example template notebook.
Right.
That's the right one. Yes. Okay. So if ours was almost a carbon copy of that one with a few minor changes that we put in, but that's I would take that template and do exactly put your code into that template, and it gives you all of the debugging that you saw.
Yeah, just to dig into that a little bit. So you can run a TFX pipeline completely on cloud in your web browser just using Colab. So there's like nothing to install in your system. You could also just run it on your laptop and just run everything locally on your laptop, and use an IDE to set breakpoints and things. So there's a lot of different ways in development and debugging to work with a pipeline and sort of a scaled down level before you push it up to a larger deployment.
Cool. I see there are no more questions from the audience, and I actually know you're back tomorrow for another talk on best practices, Reza. So maybe we should allow you to get some sleep.
Thank you, everyone.
I want to thank you guys for joining us, and yeah, on to the next talk then.
All right. Thanks.